Evidence that our universe might exist inside a black hole? What's up with that? Well, let's back up for a moment, okay? And put some base information on the table. A black hole is a region of space and time where the strength of gravity is so high that light has no path to get out of the object. All paths through space-time curve back in on itself.
So why would serious physicists entertain the notion that a universe could be born inside a black hole? When we follow the mathematics of gravity to its limits, horizons don't behave like simple walls. They reorganize what future and elsewhere even mean. Inside a non-rotating black hole, the coordinate we once called radius becomes more like time, inescapably progressing toward what the equations call a singularity. Flip that script, and a singularity can look to observers on the inside like an origin, a burst of space and time that expands away from a horizon you can never see beyond. In some quantum gravity models, the singularity isn't a dead end, but a bounce, where crushing densities trigger new space-time to inflate, decoupled from the parent cosmos. Black holes, then, aren't merely endpoints, they're potential gateways to beginnings. That's rigorous speculation, not fantasy. But rigorous speculation only matters if it can be sharpened by evidence. What, in principle, could we observe from inside that would reveal such an origin? What, in principle, could we observe from inside that would reveal such an origin? First, we'd look for imprints of the parent, preferred directions, residual rotation, or curvature that can't be erased by later cosmic evolution. A rotating black hole, for example, might seed a tiny cosmic vorticity. Yet the observed universe is astonishingly isotropic. Any global swirl is constrained to be extraordinarily small. We'd examine spatial curvature. Interior solutions often predict strong curvature, but observations tell us space is nearly flat. Inflation explains that neatly, so would a sufficiently violent bounce. We'd search for a distinctive pattern in primordial gravitational waves. Inflation predicts one spectrum. Alternative bounce scenarios predict another. Upcoming detectors may discriminate. Crucially, no observation inside our horizon can reveal the external parent, because horizons sever causal contact by definition. That's not a cop-out. It's a statement about what questions are even meaningful. If it's so hard to test, why keep the idea at all? Is it doing any scientific work? If it's so hard to test, why keep the idea at all? Is it doing any scientific work? Yes, by reframing puzzles with new constraints. The information paradox asks whether black holes destroy information, contradicting quantum mechanics. If gravitational collapse buds off a new expanding region, information doesn't vanish. It migrates. That's not a solved problem, but it realigns debates toward how horizons store and transmit data, consistent with the holographic principle. The idea that the boundary of a region encodes its interior. The universe in a whole view also clarifies the arrow of time. Collapse increases entropy. A bounce inherits a low entropy state relative to its future, and expansion does the rest. And then there's a bolder move, cosmological natural selection. If each black hole spawns a new universe with slightly tweaked constants, then universes that make more black holes reproduce more. That hypothesis, unlike many multiverse musings, risks numbers. It suggests measurable correlations between fundamental constants and the efficiency with which massive stars collapse. Do the numbers in nature actually hint that black hole making is favored? Do the numbers in nature actually hint that black hole making is favored? So far, not decisively. One concrete prediction was that the maximum mass of neutron stars should sit just low enough that many stellar remnants tip into black holes. Observations have found neutron stars of about 2 solar masses, and possibly a bit heavier, pushing against the low ceilings that would maximize black hole production. Change nuclear physics within plausible ranges, and you don't obviously crank out dramatically more black holes than we already see. Star formation histories, supernova mechanisms, and metallicity evolution all matter, and the data don't point to constants tuned solely for black hole yield. On the other hand, our universe has no difficulty making them. Supermassive ones at galactic centers, stellar mass ones by the millions. That abundance keeps the door open, but it doesn't close the case. Here's the payoff. whether or not our cosmos began inside a black hole. Horizons are the organizing principles of modern gravity. They tell us that inside and outside are about causal access, not mere location. The entropy of a cosmic horizon scales like a black hole's. The thermodynamics of spacetime seems universal. Thinking of the Big Bang through the lens of horizons disciplines our questions. It demands testable imprints, curvature, isotropy, gravitational waves, while reminding us of the limits that nature imposes on what we can know. Inflation remains our most successful account of early universe data. Black hole-born universes haven't earned that status. But the exercise isn't wasted. It sharpens the boundary between mathematics we can confirm and stories we simply enjoy. In science, even the most cinematic ideas must report to duty with predictions. Until they do, we can stand at our own horizon, the observable universe, recognize why it is a boundary of knowledge, and let that humility be the most reliable guide to what comes next. Like if this was interesting, and hit the subscribe for more.